Hello everyone, my name is Samuel Dembowitz and today we'll be talking about Lab 4, Circuits and Capacitors. The goals of this lab were to demonstrate the conservation of energy within circuits. We utilized the loop rule and the node rule to analyze circuit components. Loop rule you can see here, and the node rule you can see here. We also analyzed the function of capacitors in circuits when they're charging versus discharging. The first part of this lab had us predict the flowing current through a circuit by utilizing the loop rule. Here we have the EMF of the two batteries plus the resistance total, since the two resistors are in series, times the current, equal to 0, and we solve for this current here, which is verified in the ammeters. And the next part of the lab had us connect a voltmeter to an open circuit, as you can see here, and see how the circuit responds. We can see that the voltmeter reads 3 volts, which is a result of being connected to the two batteries, but the ammeter reads 0 because the overall current is 0 in the circuit since it's open. Next, we calculated the potential differences among many different parts of the circuit. You can see one example of it here, and you can see all my data here. And the sum of these voltages is equal to 0, which satisfies the loop rule. I then plotted this data here to see the voltage over the different parts of these circuits. The lab then asked us to calculate the actual resistance for the two resistors, the wire, and the ammeter, which was accomplished through Ohm's law, V equals I times R. After that, we created a parallel ammeter circuit, which you can see in the picture here. And normally in a parallel circuit, current gets split between the two paths, changing the reading on the ammeter since the current will be different. However, since the ammeter has 0 resistance, this means all the current avoids this 100 ohm resistor and creates the same current reading on the two ammeters, since the current in this area is equal to the current in this area. The second part of this lab had us utilize capacitors that were charging and discharging and observe their behavior. As time progresses, for both cases, the light bulb dims and current slows down until it stops. However, we notice that when it's discharging, it flows in the opposite direction to when it's charging. When it is charging, the capacitor is becoming polarized, as you can see by the plus and minus charges on the plates, versus being discharged, it's becoming neutral. We took some data for when a 10 ohm bulb, a 20 ohm bulb were in the circuit, and recorded that data as you can see there. Then we were asked to calculate the RC value by graphing natural log of voltage divided by the voltage times 0 for 0 to 20 seconds. You can see the data in this table here, and you can see the graph here. We used this linear approximation to calculate our RC value, which we found to be 6.8 seconds. Then we compared that to the RC expected value, which is resistance, that's 30 ohms, times the capacitance of 0.02 farads, to find that the expected value is 6 seconds, which means that despite some human error in calculations, we were pretty close to the expected value. Lastly, we were asked some discussion questions about if we were doing the lab in real life. If we were using an actual ammeter, then the ammeter would have a small amount of resistance, meaning that the current readings would be slightly lower than what we found in the model. If we were using a real battery to charge a real capacitor with no resistor, the model would predict that the capacitor would charge immediately, but real-life objects have some resistance values that would slow the charging process. Thank you for watching.